13.1. Newton's Law of Universal Gravitation. The outline of this video is as follows. We will begin by exploring the foundational idea behind gravity, Newton's insight that attraction is a universal phenomenon. From there, we will formalize this concept by introducing the law of universal gravitation, first in its simpler scalar form. We will then discuss the crucial constant that appears in this law, the universal gravitational constant, known as big G. Next, to handle forces in multiple dimensions, we will develop the more complete vector form of the gravitational force. Finally, we will wrap up by summarizing the key properties of this fundamental force of nature. Newton's great insight was that the force of gravity is universal, meaning the same physical law governs both an apple falling to Earth and planets orbiting the sun. The famous story of the falling apple illustrates this leap of imagination. Newton proposed that the very same force pulling the apple downward was also the force keeping the moon in its orbit around the Earth. This was a revolutionary idea because, for centuries, it was believed that the heavens operated under a different set of rules than the Earth. Newton's assertion unified what were called celestial and terrestrial mechanics into a single framework. He formalized and published this groundbreaking work in 1687 in his treatise, Mathematical Principles of Natural Philosophy. The essential concept here is that Newton proposed one single law of gravitation that applies to all objects, everywhere in the universe. This slide introduces one of the most fundamental laws in physics, Newton's law of universal gravitation. This law describes the attractive force that exists between any two objects that have mass. The law has two main parts. First, the force is directly proportional to the product of the two masses, which we can call m1 and m2. This means that if you increase the mass of either object, the gravitational force between them increases. Second, the force is inversely proportional to the square of the distance, r, between their centers. This means the force gets weaker as the objects move apart, and it does so very rapidly. We can express this relationship mathematically. The magnitude of the gravitational force, F sub g, is equal to a constant, capital G, multiplied by the fraction m1 times m2 over r squared. Because the force depends on 1 over the distance squared, this relationship is called an inverse square law. For example, if you were to double the distance between two objects, the gravitational force between them would drop to 1/4 of its original value. The essential idea is that gravity is a universal force whose strength is determined by the masses of the objects and the distance separating them. The symbol G in Newton's law is the universal gravitational constant, which is a fundamental value that sets the strength of gravity throughout the universe. Its value in SI units is approximately 6.674 times 10 to the power of -11 Newton meters squared per kilogram squared. This extremely small number shows that gravity is an inherently weak force, which is why we only notice it when very large masses, like planets, are involved. This constant was first measured experimentally by Henry Cavendish in 1798. He used a very sensitive instrument called a torsion balance to detect the tiny gravitational pull between lead spheres in his lab. Interestingly, Cavendish's primary goal was not to determine G, but to use his results to calculate the density of the Earth. It is important not to confuse this universal constant, capital G, with the local acceleration of gravity on Earth, which we call lowercase g. So the universal gravitational constant G is a very small number that quantifies the weakness of the gravitational force. Since gravity is a force, it has direction, and we must express it as a vector. To do this, we define a unit vector, which we call r hat 1, 2. A unit vector is a vector with a length of 1, and its only job is to point. Here, it points from particle 1 toward particle 2. Now we can write the full vector force that particle 1 exerts on particle 2. As the equation shows, this F vector 1, 2 is the magnitude we already know, g times m1 times m2 over r squared, multiplied by the unit vector r hat 1, 2. The negative sign out front is the most important new piece. Since gravity is attractive, the force on particle 2 pulls it back toward particle 1. This is the opposite direction of our unit vector, so the negative sign correctly describes an attractive force. Finally, Newton's third law confirms that the force particle 2 exerts on particle 1 is equal in magnitude and opposite in direction, so the vector F21 is just the negative of the vector F12. Now let us explore three key properties of the gravitational force. First, gravity is a field force, meaning it acts over a distance through empty space. Unlike some other forces, it does not matter what medium, if any, separates the two masses. The attraction is always there. Second, the force follows an inverse square law. This means the force weakens very rapidly with distance. For example, if you double the distance between two objects, the gravitational force between them becomes 1/4 of its original value. A third property is a very powerful simplification. For any object that is a spherically symmetric mass distribution, like a planet, you can calculate the force it exerts on an outside particle as if all its mass were concentrated at its center. This allows us to find the force on a particle at the Earth's surface by using the total mass of the Earth, m sub e, and the Earth's radius, r sub e, as the distance. The force F sub g equals g times m sub e times m, all divided by r sub e squared. Therefore, we can treat a massive planet just like a point particle for objects outside of it. Let us take a moment to clear up a very common point of confusion in this topic: the difference between lowercase g and uppercase g. Lowercase g represents the magnitude of the free fall acceleration. This value depends on where you are. For example, near the surface of the Earth, it is about 9.80 meters per second squared, but it gets smaller as you move farther away. So g is a local value. Uppercase g, on the other hand, is the universal gravitational constant. It is a fundamental constant of nature with the same value everywhere in the universe. The key takeaway is that lowercase g is a variable acceleration, while uppercase g is a universal constant. Now let us test our understanding of the force law with a quick quiz. A planet has two moons of equal mass. Moon 1 is in a circular orbit of radius r. Moon 2 is in a circular orbit of radius 2r. The question asks for the magnitude of the gravitational force on Moon 2 compared to the force on Moon 1. Remember that the gravitational force is inversely proportional to the square of the distance. Since Moon 2 is twice as far away, consider how that affects the force. Please pause and select your answer. Now we will apply the law of universal gravitation to a situation with more than two objects, which requires us to use vector addition. In this example, we have three identical billiard balls, each with a mass of 0.300 kilograms. They are placed at the corners of a right triangle. Our goal is to calculate the total gravitational force acting on the cue ball, which we label as M1, due to the other two balls, M2 and M3. Conceptually, the cue ball is attracted to ball M2, and it is also independently attracted to ball M3. This means there are two distinct force vectors acting on M1. To find the net effect, we cannot simply add the magnitudes of these forces. Instead, we must perform a vector sum. The key principle is that the total gravitational force on an object is the vector sum of the individual forces exerted on it by all other objects. Now we will calculate the individual force vectors acting on the cue ball, M1. First, consider the force from ball M2, which we call F21. Since M2 lies on the y-axis, the attractive force it exerts on M1 is directed purely along the positive y-axis, in the j-hat direction. We apply Newton's law of gravitation, the universal constant g times M2 times M1, all divided by the distance, a squared. Plugging in the values gives a force vector of 3.75 times 10 to the power of negative 11 j-hat newtons. Similarly, the force from ball M3, called F31, is directed along the positive x-axis, in the i-hat direction. Its magnitude is g times m 3 times m1, divided by the distance, b squared. This calculation yields a force vector of 6.67 times 10 to the power of negative 11 i-hat newtons. The net gravitational force on the cue ball is simply the vector sum of these two individual forces, giving a final vector with both an x and a y component. Now that we have the x and y components of the net force, we can combine them to find the force's total magnitude and direction. To get the magnitude, we apply the Pythagorean theorem. The magnitude F is the square root of the quantity f sub x squared plus f sub y squared. Plugging in our values gives a magnitude of 7.66 times 10 to the power of negative 11 newtons. To find the direction, we calculate the angle theta that the net force vector makes with the positive x-axis. The tangent of this angle is the ratio of the y component to the x component. Taking the inverse tangent of this ratio gives us an angle of 29.4 degrees. The most important result here is the magnitude. This force is incredibly small, confirming that for everyday objects, the force of gravity between them is so weak that it is completely negligible. Let us summarize the key features of Newton's law of universal gravitation. The fundamental idea is that every particle with mass in the universe attracts every other particle. The magnitude of this force, F sub g, is given by the equation g times the product of the masses, m1 and m2, all divided by the square of the distance, r, between them. This relationship is often called an inverse square law. To describe the force as a vector, we note that it is always attractive. The vector force F sub 12, which is the force on particle 2 from particle 1, is equal to negative g times m1 square meter over r squared, all multiplied by the unit vector r hat sub 12. The negative sign is important, as it indicates the force pulls particle 2 back toward particle 1. The proportionality constant, g, is the universal gravitational constant, which has a measured value of approximately 6.674 times 10 to the power of negative 11 Newton meters squared per kilogram squared. This framework allows us to calculate the gravitational force between any two masses in the universe. This question asks us to explain the meaning of the negative sign in the vector equation for gravitational force. This sign is fundamentally important because it tells us about the nature of the force itself. To understand it, let us break down the vector components in the equations. The term r hat 1, 2 is what we call a unit vector. By convention, it is defined to point along the line from mass 1 toward mass 2. The vector F12 represents the force that mass 1 exerts on mass 2. The negative sign in the equation mathematically reverses the direction of the unit vector. This means the force vector, F12, must point in the exact opposite direction of r hat 1, 2. So if the unit vector points from mass 1 to mass 2, the force on mass 2 must point back toward mass 1. A force that pulls an object toward another is, by definition, an attractive force. In short, the negative sign is the mathematical way of stating that gravity is always an attractive force. It always pulls masses toward each other.